Okay. Well, thanks for the introductions, everyone. It looks like I have a transcript going here too. Let's see if I can turn that off. And so, yeah, with that, I think let's get into the presentation. So go ahead and share your screen.
Yep. So, I'm gonna go over very briefly about our research efforts on the side effects in DPS. So I'll first give very brief background about DPS. I'm not sure how well we know the audience know about the DPS, but I will give very brief introduction and then describe the side effects in terms of the lab testing setup and what is the source of side effects and how we do experimental and numerical modeling on the side effects. And then we talk about some antenna calibration work that we are facing some issue on that part, and we hope that to get some feedback from the GPR manufacturer. And then the last, we open some discussion points. And for DPS, basically we are it's a density assessment technology for asphalt pavement, and it's capturing the air voids through inverse calculation of dielectric property of the material, and we are using the GPR to calculate or measure the dielectric. So the figure on the bottom is a demonstration of the technology that it offers a full coverage and fast estimates of the air voids of a pavement, and this is a project we have done in a highway in Greenbelt, Maryland. And the figure on the right top is the way that we do inverse calculation about from dielectric to the air voids. So this study will only focus on how we measure the dielectric. And in terms of dielectric measurements, we typically have two methods. One is surface reflection. So in the surface reflection, we measure the reflection coefficient. And for non-magnetic materials like asphalt, and if we have air launching with the normal incidence, and we kind of use this simplified version of the equation to calculate the dielectric. But sometimes this angle might not be negligible, then we move to this equation to calculate the dielectric. And for the time of flight or two-way travel time, we kind of measure the travel time difference between the surface reflection and the bottom reflection. So through some calculation, we can basically using this kind of complex equation to calculate the dielectric based on the time difference. But for air launching tests with normal instance, we can simplify to this version, which is commonly seen in the paper and the reports. So we move to the lab testing setup. So for the lab testing, it primarily provides the dielectric measurement for field course or laboratory gyratory samples. We call them pucks. And from that, we can develop calibration curves based on the measurement of the pucks. So current practice, we require taking course from the field. So these efforts, we can kind of mitigate that issue or efforts. So we take advantage of the lab testing and develop the calibration curve. So we can, in the field, we basically employ those equations in the field directly. And this is the picture of basically from GSS lab testing RDM2. So in the lab test, we have a specific testing procedure presented by Kai's paper in 2019. Basically, from step 1 and 2, we isolate the surface reflection. From step 3 and 4, we isolate the bottom reflection. And based on that, we can kind of identify the travel time difference, and we use the time of flight or two-way travel time to calculate dielectric. It is possible to also use the surface reflection, but the previous work, especially Kai's work, showing that the two-way travel time might be more robust. So at this moment, we kind of focus on this two-way travel time. And in the future work, we plan to also investigate the surface reflection method as well in this testing setup. So regarding the size effects, it's because our parks or cores are limited with the size about 6-inch diameter, which is about 15 centimeters. And because of that, during the time domain or time duration of the data collection, we might have some unwanted signals, such as the reflection from the edges and sides that will accompany with our interested signal, which is the surface and bottom reflection. And this figure is basically the results from Kai's paper, and it shows that with different sample thickness, the time of arrival or of different signals is kind of different, but in the region that we normally have, which is around 8 to 10 centimeter, there are a couple of signals that might accompany with the bottom reflection, which might change your dielectric measurements based on the time of flight or two-way travel. And we call that the change in dielectric due to the limited size as the size effects. So our research is more like investing if we can change the size or the diameter of the park, can we change the thickness to avoid this kind of issue, or that's the direction to go. So we first did a experimental test with a slab. So we basically built a sufficient large slab to avoid potential edge effects. So in this slab, you still have the edge effects, but the timing will be much later than the bottom reflection. So we kind of assume that it won't influence your dielectric measurements. And we follow the same testing procedure and get the dielectric measurement, which is around 5.14. And then we take a core in the middle of the material and then take the same measurement and found we observe a kind of significant difference between them. It's a negative 0.108. It's larger than the Ashto spec limit, which is around 0.08. And in this case, the sample height is around 18 millimeter. In the meantime, we actually did some numerical study and showing that if we increase the height of the sample, the edge effects might be lower. And then so we did another test with 106 height or thickness, and we repeat the same measurement, and we found that we do observe a less significant value of dielectric change, and this value will be within the Ashto spec limit. So this is about the numerical modeling that we use GPR max, which is a finite difference time domain method. We built a parallel models. One is with actual specimen size, and one with infinite long size, so you don't have edge reflection or diffractions from the edge to influence your surface or bottom reflection. So the difference between the two models will be the size effect. So we kind of model them, follow exactly the same testing or lab testing kind of procedure. We start with step 1, Darling spacer plus Darling spacer, and step 2, Darling spacer plus the metal plate. For the metal plate, we can set the dielectric of them to be infinite. So it's kind of so for step 3 and step 4, we model with Darling spacer plus sample, and the Darling spacer plus sample and plus metal plate. So we follow that, and this is kind of a calculation breakdowns. We can successfully identify the surface reflection and isolate the bottom reflection. And based on the first negative peak, we can calculate two-way travel time. And based on that procedure, we can calculate the dielectric of the sample. That's pretty much of the testing setup. And we can compare the two models. In this case, the black solid line is the model with size effects. So in that model, we build actual size of the sample. And the red solid line is the parallel model, which we build them with infinite long size and to avoid the side effects. And the difference between the two will be the side effects that might be the reflection from the side surface or critical diffraction from the edge. And we observe that you probably don't have the edge effects won't affect the surface reflection, but it will affect the bottom reflection. And the side effect might arrive earlier than your first negative peak. And because in reality, the measurement will be the superposition with the bottom reflection plus edge effects. So if we are trying to use two-way travel time, the peak value, uh, either the first negative peak or the first positive peak, the peak timing will be shifted because of the superposition. And that is basically the mechanism of why the edge effect will influence your um, dielectron measurement.
So
And
the black is if you had an infinitely wide
the black is the one with actual size.
with the actual size, and then the red
Is the one with infinite long.
infinitely. Okay, and then the dotted green line is the difference between the two. Okay.
It's basically the subtraction.
Okay.
And this figure is basically a summary of the results. So we investigated three dielectric of the sample, 4.5, 5.5, and 6.5, which is kind of the range of asphalt. And the green triangular represent the 2 points that we did the experiment testing with their dielectric around 5. So based on the results, we can see that in a region below 80 millimeter, we potentially have significant side effects or change in dielectric because of the reflections that from the side or edges will influence the bottom reflection and change the timing. And if you have a sample height greater than 100 or near 120, which is kind of preferable, which that you can mitigate this edge effects within the acetone limits. And that's the initial basically come out with the study. Kind of agree with Kai's other projects. But in this study, we used a theoretical antenna, and we are trying to see whether we can calibrate the antenna and make the numerical study results more close to the practice and convincing. So we start some antenna calibration efforts. So we start with the GSSI's website. In their website, they claim the sensor center frequency as 2 gigahertz, and we kind of test the antenna. The first one with different scenarios, and the first one is the open space, which is kind of getting the direct coupling of the sensor, and we do a FFT, and we get a peak around the 2.0 gigahertz, which kind of agree with the website. And then we test the steel plate reflection, but we get another, slightly different values. For a third scenario, we do the calibration test with using the lab kit and the Darwin calibration block, and we isolate the surface reflection. The time domain signal looks like this, and then we do FFT, and the peaks will be shifted to the right, to the left. We get 1.78, and for the same test, we isolate the bottom reflection, and we get a peak around 2.44. So basically, we get very different peaks for different scenarios that are, kind of different from the manufacturer's spec. So which kind of give us a hard time to compare our experimental and the simulation results. We dig some theoretical background of why that would happen. So for Fourier transform, we normally get the magnitude spectrum of the time series signal. If we have a time shift on the original time signal, this time shift might be a phase shift between different dielectric properties, or just the travel distance is different. Your magnitude spectrum would not change. So that's normal. Normally you see it in textbooks saying if you have a time shift in the time domain, that would not change your magnitude spectrum in frequency domain. But in our DPS, this is not the case, because in our case is more like you have a signal arrive earlier, and you have the, similar signal with the kind of close frequency content arrive later. For example, in this case, you probably first have a direct coupling, and then you have the surface reflection. They have a travel distance different, and then you have a arriving time difference and a time delay or time shift. And then you plus them together, which is the case that you get data in your sensor, and you do FFT, and you will find that their magnitude spectrum will change, and that change will related to the frequency and the amount of time delay you have in the signal. And this term will be limited with between 0 and 2, which is kind of significant to your spectrum. Here is an example that assume you have a single sine wave and you do FFT, and you found that you get a peak that is exactly the same as your assumed signal. But if you have the same signal, but you have a 2 pi, half pi time delay, and this is what it looks like in time domain. Because of the 2 pi time delay, the negative part and of the first wave and the positive part of the second wave will be canceled, and you get a very different FFT. So this kind of theoretical investigation might explain why we get different FFT peaks for different scenarios of the DPS. So our next step, we plan to use finite element modeling to model the antenna, but it seems like it would be a very time-consuming and difficult task, because we don't know what exactly inside the structure of the antenna unless we open the case. So this is the work that the GPR Max author have done in his PhD dissertation back to 2009, and they did some work using the GPR Max to calibrate the GSSI's 1.5 gigahertz, but that's only for that case. They don't publish other frequencies, so we kind of have this issue in calibrate our model. So in the same time, we investigate other, effects might change the edge effects, such as the type of our input voltage signal. So in our original numerical modeling, we use the recur signal, which is a negative second derivative of the Gaussian, looks like this. And then we change that to the first derivative of Gaussian. And we repeat the calculation. We found that the first derivative of Gaussian can kind of mitigate these edge effects better than the recur. So the solid line in this case is the recur for the three types of dielectric, 4.5, 5.5, and 6.5. And the solid line is the case with using the Gaussian derivative, or the first derivative of Gaussian. And we find that even in the region that you might have edge effects, if you change that to the first derivative of Gaussian, that actually might be able to limit it to within the limit of Ashton spec. So in this case, it means that in some case we cannot change the sample size. We probably can change the antenna to mitigate this issue. That's some of the takeaway from this work. And then we kind of increase the center frequency of the test setup. For the two kind of wave, we increase the center frequency to 2.5, and we observe that the edge effects can be effectively mitigated even with the region you possibly have. But if you reduce the center frequency to 1.5, and in those regions you get worse edge effects and you get a larger difference. And even in the region that we expect you not to have edge effects, because of the change of the center frequency, you introduce actual edge effects in that region. And this happens both for the Ricker and the derivative, Ricker and the Gaussian derivative. But relatively, the Gaussian derivative is more robust than the Ricker.
Hey, since Roger is here, so my understanding, Roger, the center frequency for the antenna is 2.7 gigahertz. Correct? Correct me. I thought I overheard from either from you or from somebody else.
You're on mute, Roger.
I was hoping nobody would hear me.
Uh,
Yeah, it's it all depends on how you window it, and marketing in the real world, marketing likes to have a slightly higher frequency. So one way to measure frequency is to, when you have your Ricker type wavelet, measure the first negative peak and then the second negative peak, and convert that time into frequency. And that gives you a nice ballpark center frequency. So I think it's kind of cheating a little bit, but it's an easy way for everybody to measure something. So I think Heng's analysis here really shows us what our center frequency is.
okay, so it's about 2. So,
Yeah.
okay. All right. Good. Thank you.
Thank you, Raga. So this figure is basically to summarize the effects of center frequency, and I filtered out other signals and to show you that only in the Ricker 4.5 case, and you can see that the solid line is the original case that we investigate the 2.0 gigahertz, and if we increase to 2.5, the edge effect is narrower. And if we decrease the center frequency to 1.5, you can have a severe or worse edge effects on both sides. So it might be a good solution that if we can, in some cases, we can't change the sample. We can possibly change the antenna spec to mitigate this issue. And then this is the case for the Gaussian derivative. If I filter out only for the 4.5 case, you can actually get the similar pattern for other case. I just for simple that we can see similar pattern for the Gaussian derivative, and the increasing the center frequency, you can actually narrow the dialogue change because of the size effects, and will be within the limit of Ashto spec. So the remarks from this study is that we kind of verify that the edge effects you might happen in the park samples or cross samples, and if we can increase the height that normally higher than 100 millimeter, so you can mitigate this issue to within the limit. But we plan to fabricate more slabs so we can verify our study results with more experimental points. Now, a second point is that the simple FFT would not characterize the antenna correctly, simply because of the time shift, and we are not receiving a simple signal. We might collecting reflections from multiple sources, and that time shift will change or shift the peak of your FFT and would not characterize the actual center frequency of the FFT. And we also did the numerical modeling of the side effects that might change by the input voltage signal. For example, if you change from Ricker to Gaussian derivative, you probably have less edge effects. And if you can increase your center frequency from 2.0 to 2.5 gigahertz, the issue might also be mitigated. So so those findings may suggest that in the future DPS implementation, where we don't have samples of cores that meet the site requirements, we potentially could change the antenna to mitigate this issue. So this is where we can start the discussion. It might not be just focused on this, but we just open some points that we can start. One is the antenna calibration. So we would like some suggestions how we can better model the antenna so we can improve our numerical modeling. And we can discuss how we can collaborate with each other to share our information and research in the future.
Thank you very much, Heng. That was informative as always, and I'm excited to get into the application aspect of these things, but I think it's probably better to start with clarification type questions, and making sure that we kind of understand the assumptions that went into these simulations and the results that way. So I think maybe to start, either Roger or Jacopo, if you have any questions about kind of the boundary conditions and clarification questions about the simulation work or the laboratory setup too for those data points.
I can start.
Okay.
And when you made those measurements with the asphalt block and then cut out the centerpiece and you got the difference in dielectrics, were the dielectric values calculated using the DPS setup or the lab setup using our calculations?
So yes, we follow this procedure, but we are not using the built-in software because we kind of so in the last TRB, you remember we asked you to share the code that we can get the actual A scan of the RDM2. So we use the RDM2 and that script to get the A scan, the raw A scan, and follow the steps and using this equation to calculate the dielectric. So we do compare our method with the built-in method for the calibration test, the calibration block, and we do get the very close results.
Calibration block. You
Oh,
mean
which is this one.
That one.
Yeah.
Well, our calculations are a little bit different than yours, I would think. It would have been good to actually just see what our dielectric values are compared to what you calculate. If you could do that going forward,
Sure.
I think that would be really helpful. One of the things we do is we do a very careful peak fitting of that first arrival. Very important. And how the background scan is subtracted from the other scans is also pretty important. So I'd be curious to see if there are any differences. But I'm not surprised with your results, though. I think early on, we made a lot of measurements with fiberglass blocks of different thicknesses, and we were getting a little variability there when we got down around 7-8 centimeters, and that seems to pretty much explain why we were seeing what we did. Besides that, though, I don't have any other questions regarding your analysis. I think it was really thorough.
Thank you. We can remeasure because the slab we already core them, so we can't repeat test. We can repeat the test with this course, and then compare the results and send you the updates later.
Okay, thank you.
My turn, I guess.
Yes.
Yeah. Okay. I have just a couple of questions here. I mean, we have a bit of a different animal as a system, so, but I'm curious. So, I'd like to. So when you're looking at the size of the packs against the slab here, so first of all, the limit for the, in terms of complying with AASHTO and staying within those limits, you're looking at the difference between measuring the infinite and the core, or a slab and the core. So when you say we need to be within there in the variability, what are you measuring against?
So in this case, so in the experimental testing, our focus is the difference between the slab and the core. But in the numerical modeling, we kind of compare the actual size versus if you have infinite.
Versus infinite. All right.
Yeah. So in theory, these two are the same because we kind of calculate the slab size. They still have the edge effect, but the edge effect will arrive much later than the time window you calculate to capture the bottom or surface reflection. So we assume that part won't change the results.
Okay, and in terms of these edge reflections, that's the only phenomenon that you have considered, and that's based on your assumption that is the only phenomenon that might occur, or
yeah, that's a good question. So for here, we focus on the edge effects. So because we get some feedback from our other researchers, and we ourselves also think that it might happen. So that's but it also have other parameters to influence your dielectric measurements, such as your mix design and other parameters.
No, but I was talking just about arrivals that can shift your estimation actually in time of where the bottom would be, right? So
maybe Heng, can you put the previous, yeah, that one, pull that one up, because then maybe we can talk about it from that perspective.
Yeah, and also the one with the wavelets, I think that one was interesting. I think it happened later on or before, I don't know. But there is one thing that I would have liked to hear to I think it's missing a bit. So you have not considered really the effect of Fresnel zones in this. And since you're talking about a limited specimen against a very wide specimen and then an infinite specimen in terms of measurement, what happens there, you have Fresnel zones, so you have areas where the signal arrives and it adds constructively. And then you have an area where the signal arrives and this still from the bottom of the slab and arrives negative. And that subtracts. And that also does explain why you see basically in your simulation a variation between, you have something that is very strong when what you're measuring is finite in size against something that is very small when it's infinite in size, right?
Right.
And that tends to shift your arrivals because they do arrive at different times, ever so slightly, before the Fresnel zones, basically the components that arrive from a larger radius at the bottom of the slab.
Yep.
And these ones, then at a certain point, they lose amplitude enough so that you can just don't care about them anymore. But I wonder how much that actually is influencing your results rather than the side effects. Because and that is also kind of consistent with the fact that if you have a larger distance, then what you're doing is that your cone of electromagnetic waves is spreading wider. So the first Fresnel zone where everything arrives in constructively is wider. So you have a less you have a minor distance in the electric as measured because of the arrival time of the bottom of the slab between the puck and the slab that contains the puck. So that is also consistent. So I wonder if you consider this and measured against the side effects of the slab, what is actually stronger? Because the second Fresnel zone, which is negative, is pretty strong, is actually very strong. So I wonder how much that is actually influencing your results rather than the side effects.
So in this case, we haven't plot the Fresnel zone in this special test hub. We assume that, but the concept of Fresnel zone is basically the superposition of different source that based on the peak, either the first, is constructive or deconstructive way you define the Fresnel zone. In here, it's the similar concept. The edge effects, is the source that you have superposition from with the actual bottom reflection, and that is not exactly the first or second Fresnel zone. Is somewhere between them. You may also influence the peak, because when we get the peak signal, we are actually getting the first derivative of that point to be 0, right? And then you superposition with other functions. Either that functions can be large or small. Their derivative can still be large, and that will be sufficient to move your peaks a little bit or not. As long as your peak moves, your time of arrival or two-way travel time will be changed. Your question is good that we should plot the first or second Fresnel zone to make sure that the consideration is the.
I think it's worth. What I'm saying is basically
right.
worth measuring it, right? So you're always going to move in the first Fresnel zone because the thing is small. That's what is going to happen.
Right.
It's small enough to be within the first Fresnel zone, but what happens is that as you enlarge it, as you stay in the slab, basically that you're going to move within the first Fresnel zone anyway.
Right.
So you're having more. It's going to add more and more and more before you hit the second, because you're never going to in the practice of the slabs. But when you're going into modeling, you're going for the infinite slab. That's for sure hitting the first negative. So the second Fresnel zone.
But the thing is that when we have infinite long size, we set the boundary. See, we show here is the absorbing boundary, which means when your wave reaches to here, will be damped out. Then there will be no reflections. That's how we consider this part.
Yep, but you see that you have more effect of the second Fresnel zone in the infinite against the slab. So if you're trying to figure out which of the two.
That might be the reason why we got different results between the experiment and simulation. And thank you. We will consider that in our future work.
And maybe just one question more is why the Ricker or the Gaussian there? Why did you model with that? Is it similar enough to the wavelets that you find in practice, or?
You mean why I choose Ricker or? That's a good question. I read a lot of papers, and many papers mention Ricker, and that's why I choose Ricker, because I actually don't know how manufacturer design the system, but many papers mention that this is a good approximate. And also many people mention this derivative of Gaussian. So I just tried both of them and get different results. And that's pretty much it.
How we manufacture them, we do an antenna and we hope for the best. That's it.
So yeah, I hope we can get some answers from or insights from your end. And
yeah, maybe Roger can Can you give us hints on which one you used it or voltage, input voltage?
Well, our waveform shape is closer to the first Gaussian derivative, but it's not exactly that. So, yeah, it's like Jacopo said, it's whatever it turns out when you make your antenna. Yeah.
There is always some spurious, right, Roger? That's unavoidable. But yeah, I would say that the reticle of the Gaussian is what mostly you would find in GPR in general. I think that's fair to
So you're
say,
saying this one
especially
is more
pops.
popular?
It's not popular, it's just what happens most of the in practice, I think. Closer to that. It's never going to be as clean, of course, but.
So that's what simulation shows. It's better to use the derivative of Gaussian, right?
Yeah.
Oh, great questions, guys. So I think it would be good to talk a little bit about kind of application, how we can try to take advantage of this type of tools and research to advance our method and make it something that we can not only just understand more, but use in a way where we're able to help out with density analysis. So I had a few thoughts in that direction, and one of those being, you talked about the time shift being caused by a superposition of arrivals potentially, and while I have you guys here, I'm just curious if there is a potential, if we do this type of analysis, kind of the simpler thing to do, which might still be really hard, is to analyze our arrival time that we get. One example would be specifically from the bottom of the puck, if we're doing this exact experiment that Hang's talking about, or I can even think of potentially using it for an air launched surface reflection based measurement, if we can do some of this kind of an analysis as a goodness of the signal type analysis. So that would be to say, if we know we have a 2 gigahertz center frequency signal when we're measuring it, and then we do the analysis on our arrival, could that be possibly an indication of the goodness of or how trustworthy our arrival measurement is, or is that just too much a function of what happens after the arrival? I don't know. And then the second question, related to that is, if we get from an asphalt pavement that really satisfies our condition of being normal to the surface and relatively flat, versus one where we've gotten more uncertainty with, if it's a really open graded mix where you have maybe larger aggregate and more gaps, maybe the surface texture is affecting our amplitude of our signal. Is there a way to use these type of tools to kind of help with a trustworthiness of our signal in practice? If there's any thoughts from Roger or Jacopo or Hang on that.
Well, Kyle, from what my experience is, it really it depends on how accurately you're going to be able to reproduce the actual antenna. And anytime we talk about changing the center frequency, that scares me. Mm-hmm. Because I think it's important that we use the same antenna, same bandwidth of frequencies to measure the pucks as we do to measure the surface texture in the field. And by shifting the frequencies one way or another, then we open up possibilities of involving frequency-dependent shifts in our calculated dielectric.
Yeah.
So,
and then I guess also if it's if the bandwidth is on the higher frequency end, maybe you're more sensitive to aggregate or local changes in dielectric too, I suppose.
Possibly.
Yeah. But certainly, I think that given a system, there's potential for calibrating that system for impacts due to different thicknesses of pucks or other things, samples, so you can apply corrections. And maybe that it would be the route to go.
And can you bring up the plot that has your 2 experimental data points along with your simulations?
I mean,
so are you talking about it looks like if we can get enough experimental data and simulations to show it, that if, for example, it looks like our I always forget which one you're subtracting from which, but it looks like there could be a justification for shifting your actual measurement of the gyratory puck up to account for the boundary effects, if we could make a strong case that these effects of the boundary for these given conditions are consistent. Is that kind of what you're saying?
Yeah.
Okay.
Just a thought. Can I ask a question here, Kyle?
Yeah. Yep.
Just a thought. Follow you question. I'm not sure this is a good thought or not. So Han, can you bring up the frequency analysis? You said when you do the FFT and the friction from bottom, you get 1.7, the center frequency, right?
Yep.
It's different than the surface reflection. So I'm just wondering, can you artificially shift this one to the 2, since Roger said it's about 2 and it's kind of designed it for 2? If you just artificially shift it to the 2, would that going to change something in your calculation? Can you do that, first of all, I guess? Or could be increase the accuracy? Then you do the inverse FFT after you shift it.
I can try.
So you're talking like some sort of deconvolution where you're figuring out what signals were.
No, he said this could be influenced by many factors, like Jakob mentioned, but could be the phasor zone effects. Different waves arrive the antenna, but if we know the center frequency is a 2, then we can artificially shift it to the 2, then do inverse transfer, Fourier transfer, and then we can see what's the time difference. This is what I'm thinking. I don't know it's good or not. Then maybe we get more accurate of this calculation of the thickness or the actual constant.
But that wouldn't change so it wouldn't change your peak.
Would we shift the time? Would we change the time shifting?
It's basically will alter your results. It's not I don't think that's gonna be a correction of the curve, because this peak shift, there are a lot of reasons. It might happen, so we don't know. So you might have multiple reflections from the surface. or you might have a multiple reflection in between your the antenna box.
Yeah.
So those reflections all have time shift, different time shift, and those combination will be contribute to the total time shift in your main signal. And if we move this peak artificially to the 2.0, we kind of manually change the characteristic of the data. And I don't know that can be beneficial or harmful to the results, but we can try, take a look.
Well, what I'm thinking is because if theoretically for the perfect things, which the peak should just include the shortest distance, right? Shortest
Yes.
distance wave. But since we have phasor zone effect, for example, then you can't have frequency shift in there. But if that's no phasor zone size effects, then you would capture exactly, that's the shortest wave. That should be exactly the 2. I'm thinking.
Yeah, but if you look at the curve, so we know that the GPR we are sending a pulse, but here we kind of get a continuous signal. The rest part of them are all from the multiple reflections or other source.
Okay.
That's why it's kind of unknown, because we don't know exactly the wave, how the wave reflected others. We only know that the bottom reflection, because that's the shortest travel distance. I can think about it and how we
Okay.
can incorporate this part.
Okay, I guess the other kind of application related topic, we're down to 4 minutes left, but maybe Jacopo, if you could give some guidance on maybe how experimentally we could try to track down the effect of the second Fresnel zone and differentiate that from the analysis we're doing so far with the boundary effects. If you can give some guidance on how we might want to validate where we're getting this shift from.
Well, I would try and see basically if you as you increase the size, that's the thing to measure really, and try to have perhaps be away enough from the top, something like that. Make it a little bit deeper. It doesn't really matter since you can make up perfect conditions in the simulator. And then you would see what contributes the most. You would need to make also some calculations, of course. You need to write down some equations and see how the spread happens against how the distance to the sides happen, and also try to figure out the gradient between the two, because also what happens is that when you transition, when you have the reflection on the edge, it's never anything so sharp.
Mm-hmm.
Those ones are not cream pulses, the stuff that you get from the edge when you transition from material to air is and the fact that it's slanted and everything else. In practice, what happens is that you get, it's not a clean pulse that you get back. It's not your Ricker wavelet, even if you model it like that. If you model what you send like that, so that it should be kind of, you should be able to have a gut feeling, at least, for when one thing kicks in more than the other. And that's what I would recommend to do. So first of all, consider Fresnel zones, write down some equations on where they should be against, also offset transmitter receiver, and try to manage the depths and the sizes so that you're able to distinguish between the two cleanly. Because GPR Max is going to give you both, because that's how it's built. It's built very well to do that, actually. But also consider the fact that GPR Max, if I'm not wrong, it starts, so it's spirit elements is I think it starts from frequency domain and then it adapts the signal as if it were transmitted by an impulse system. I might be wrong here. You need to talk with the guys in Edinburgh. But because they know it better than I do. But I think it's closer to my system, to our system. It's closer to a step frequency approach in the way it generates the data that you see. And then it, because that's how the mathematics work behind the scenes. And then they make it so they shape it. That's why that, you know, the antenna shape and how it works is very important, because then you give it the imprint of the actual thing that you're using. So so yeah, but do consider that when you evaluate spectra, especially, because you'll see that is not really the same. There is a little bit of difference when you, especially when you try to measure, you know, is it 1.78 or is it 2 gigahertz? You know, just looking at the image that you have in front now, you have, I mean, the trace on the left-hand side, so that the time domain data is a bit of a mess and is very limited in time domain. So what you're going to get, and you can see it in the spectrum, it's a very wide distance between the frequency domain points, right? So you're going to have a little bit of aliasing and the oversampling in time, which is good because then you get something that is nice and smooth, but that makes it, you know, the entire spectrum goes to 10 gigahertz, which of course, you know, most of it is useless, but that's just because of the effects of sampling into time domain, right? So always keep in mind that the two things are like that. You have yeah, it's sampling and window, and it's sampling in one domain becomes a window in the other. And you can have some difficulties in evaluating where the peak in frequency domain is, if as you try to limit yourself to a very one pulse in time domain, to the limit where, you know, you're going to see in frequency domain just something that jumps up and down like this, which is kind of what sometimes you could see if you try, and you know, another plus that you have that kind of behavior, and that's because you are looking at a very limited time window, which limits your frequency domain sampling, which in turn makes it very difficult to evaluate the peaks because of aliasing. You're bringing into what happens later into what happens at the beginning. That's really what happens. So I would recommend to keep into consideration these effects, the fact that when you measure frequency peak, it might not be accurate. And also the fact, and here maybe Roger, you can chime in a little bit better than what I can, but the fact that if you take an antenna and these are coupled, you know, it's here, and then you make it closer to the medium that you're trying to measure, that medium is actually becoming part of the antenna, because you have a coupling effect, and the medium affects the antenna and makes it bigger in a way. So, and I believe that GSSI has done all their calculations in the way you measure the pucks in the lab stuff, et cetera, because that's why they come up with this, with all the gizmos and stuff that you should be using, right? I don't know, Roger, if you can or want to add something here, but.
Yeah, Jacopo, I totally agree with you. In fact, I recall that some of this work we're doing is also empirical, and we found that for our measurements, the measured bistack separation that yields the most accurate results is not the same bistack separation as we used in the calculation. The actual bistack separation is 6 centimeters, and I think in our calculations, when it's coupled to the Delrin, it's something like 4.4. So I think we need to be very careful when we have the antenna in the proximity to the Delrin, and that's also why I'd like you to compare your results with the results we get from the lab measurement kit, because I think there will be some difference.
Okay. So what you're saying is that the distance between sender and receiver is effectively smaller when it's coupled to Delrin,
Yes,
or it needs to be treated that way?
that's right.
Okay. See, this is really important information. So I'm thankful that you guys are willing to spend time with us and try to figure out.
This is very interesting. I think that,
Yeah.
but I think that one of the keys, I mean, Roger just said that, the way things should be done is that you can use theory, but then you have practice.
Yep.
And you need to use theory so that you can expect some results, right?
Yeah.
But it's never going to cut exactly in the same spot. So you just need to get it as a, guide your gut feeling with that.
Yep.
And all these things are done very nicely, and they're very interesting, and they're very important. So I'm really happy to have joined today, and that Hank, you're taking these on you. So
just to follow Jakob's thought in there, just one more question. So the antenna is about 9 inches above ground. If we try to minimize these phase zone effects, is it possible can lower antenna? Or maybe using your model to figure out what's the optimal height of antenna. Can you? I don't know. Can you do that or no?
Yeah,
See
see
which height would be optimal for get better signals and also minimize the phase zone effects.
Great.
Yeah,
well, I want to respect everyone's time. So we are 5 minutes over right now. I'm willing to stay a little bit longer too, but I really appreciate everybody taking the time to join us here. And then kind of this last part of the discussion fits in really well with our goals with the pooled fund, where you say we always need to be testing our theory and our simulations with what does it actually do in practice, because that's the primary group that is part of the pooled fund, is a bunch of guys who can do guys and gals who can do measurements in practice. So I think, this presentation on May 17th and the discussion that follows there should also be really useful from that point of view. So if anybody needs to leave now, please get to your regularly scheduled meetings. But if not, we can continue discussing too. So
I'm fine. I'm free.
Okay.
I get might have to head out. So thank you guys. Good presentation, Hing. Thank you.
Yep. Thanks for joining.
I can say a little while.
Somebody's joining now.
Yeah, I think Chuck is.
Maybe Steve.
Are you there, Chuck?
Oh. Yes, I'm here. Sorry, guys, I'm off by an hour here.
Oh, that's fine. It's Hang will be presenting again on the May 17th meeting. So
okay.
And then actually we'll have a recording of the meeting too that we'll be able to share. Yep.
Excellent.
So Hang, do you have good feedback for kind of next directions, or are there anything else you want to ask Jacopo or Roger or now Chuck?
I think I take a lot of notes from them, and they raise a lot of good questions.
Great.
Yeah.
Great.
But I do have a question for Rock. So you mentioned that the separation distance originally designed for 6 centimeter, and because you contact the During, and you found that distance actually reduced to 4.4. My question is that how did you get that number change?
Well, it involved a lot of data collection. We actually designed a little setup where we did a one-way transmission from a transmitter to a receiver on the other side. So we had independent verification of the measured dielectric. It was a lot simpler then. We didn't have to worry about any bystack separation. So we established a dielectric for all the different materials. We had different dielectric materials at different thicknesses. And then we compared the results with what we got with the two-way travel time, and looked through the calculations, and it ended up being we had to change the effective stack separation for it to work.
Nice. Thank you.
Well, great. Well, thanks again to especially to Heng and Jacopo and Roger. Really, really great stuff, guys, and we'll continue on our May 17th meeting and then try to identify the most critical aspects to try to take on with our next work plan for the pooled fund then. So enjoy your Friday, everyone, and thanks again for your time.
Thank you all. Yeah,
Thank you.
Thank you.
See you.
thank you, bye.
Yeah.